Good morning, good afternoon, everyone. It is my great pleasure to introduce Professor Jeff Bullard, who is going to be our invited speaker today. Professor Bullard joined Texas A&M as a professor in August 2019. He holds joint appointments in civil and environmental engineering and material science and engineering. Before that, and this is something I think almost everyone knows, Dr. Bullard was a materials research engineer at NIST. He received a BS in ceramic engineering from the University of Missouri-Rolla and an MS and PhD in material science and engineering from UC Berkeley. His research involves applying the principles of thermodynamics and kinetics to understand, predict, and ultimately control the evolution of microstructure and properties of materials. He is a fellow of the American Ceramic Society and the Washington Academy of Sciences. He's an editor of CCR, an associate editor for the Journal of American Ceramic Society, and he has won far too many awards for me to really get into. So, with that, thank you very much, Professor Bullard, for doing this, and it's all yours.
Oh, great. Thanks very much. Yeah, so I'm really happy to be able to give this presentation, even though um, Miami caused A&M to have an early exit from the college football playoffs, which was a little hard to watch, but frankly, I didn't think A&M deserved the ranking that they had anyway. And I was rooting for you guys after you beat A&M. I was rooting for you all the way up until the final game. And you guys did really well. So congratulations for that. Um, so I tried to gear I tried to orient this talk to roughly like a entry level or second year grad student level. So not knowing exactly what the cross section of expertise was here. So this talk may be way under your heads. And this may not be, it may be at too low of a level for you. I'm not sure, but that's the way I'm going to do it. And so anyway, you should be seeing a black screen right now. Oh, one other thing I wanted to mention is Dr. Suranini and I worked out the topic of this presentation a few months ago. I think it was a few months ago now. And at the time, I didn't realize that it happily coincides with, whoops, that went all wrong. Just a second. Uh, that went all wrong again. Wait, here we go. It coincides with, see if I can make this happen now. Yeah, there we are. So it coincided with the Artemis 2 flight that should be splashing down, I think today, it's concluding. And so with any luck, some of you are already kind of in the mindset. You've been, thinking a little bit more about activities that are going to be happening on the moon in the near future and space exploration and things like that. So hopefully this talk will have a little bit of traction from that point of view as well. So the point of this talk is to give you some ideas about ways that we're trying to prepare for a permanent human presence on the moon, which is going to happen within the next decade. Both the US and China and some other, I don't know why I can't make this thing go full screen. There we go. So the U.S. and China and other countries are preparing for lots of activity on the moon that will require, essentially a permanent human presence there. And if you haven't thought much about the moon, the reason why we're so interested in going there and staying there is because the moon has a lot of resources and is strategically advantageous both from military perspective, but also from an economic perspective. It's been estimated that the moon has more precious metals, gold and platinum, within its near surface than has ever been discovered on Earth. So we're talking about essentially trillions of dollars of economic benefit. Another thing is that especially at the lunar South Pole, there is a pretty good supply of water in the form of ice. And so NASA and other space agencies want to harvest that ice both for to support a human presence. Everybody needs water, but also as a raw material to make liquid propellant for other rocket missions to other parts of the solar system. So the moon is a relatively low gravitational potential well compared to Earth. And so if you can get up to the moon and then launch rockets from the moon, it's a lot cheaper in terms of fuel cost to get into space and go to Mars. So there's lots of reasons why we want to go to the moon. And if we're going to have a permanent human presence there, we need to be able to provide life support, habitation. We need shielding from radiation and from the thousands of micrometeoroids that are constantly bombarding the surface. It's a very hostile environment for human life. And so there's a lot of activity going on now in different sectors to find ways to engineer the lunar surface, make landing pads, roadways, houses, and things like that. So that's primarily what the motivation for this talk was. If you think about ways that we can make materials or make structures on the moon, we don't really have that many choices. And the reason is because it takes a lot of money to transport anything from Earth to the moon. We're going to be forced to use whatever materials and energy resources are locally available on the moon to be able to do anything. And so that really limits us in terms of what kinds of manufacturing methods for materials we have. So one potential way that you can think of making load-bearing materials on the moon is something that would be analogous to the way we make concrete on Earth, using chemical reactions to consolidate materials. And the crust, the near surface of the moon, is composed of a regolith material, very in some ways very finely divided, going all the way down from all the way from micron-sized particles like a powder, all the way up to rock-sized, gravel-sized things. And so we've got a lot of materials there that if we could find a way to make them react, we could make something like concrete and use the larger particles as aggregate. So that's one possible method that you could think of to make materials on the moon. The nice thing about concrete, like everybody knows, is we can make large objects out of it. If we can stick the larger particles, the gravel-sized particles in there, then we have aggregate that it helps improve the mechanical properties. We can make arbitrary shapes by casting. So those are the good things. The unpleasant things about concrete is that it requires chemical reactions to happen. And the moon is not a very fun place to try to control chemical reactions because depending on where you are on the moon, the temperature can be extremely low, like at the lunar South Pole. Some of the coldest places in the solar system are at the lunar South Pole. Or if you're at the equatorial regions on the moon's surface during the daytime, the temperature can go up to well above the boiling point of water. And so, and in addition to that, of course, you have no atmosphere. So there's basically a hard vacuum surface. So you can't keep liquid water for any length of time on the surface of the moon. It's either going to turn solid or it will boil away. We've also found out from some missions that some colleagues and I have done at the International Space Station that the behavior of concrete is greatly affected by the gravitational field that's present when you make it. We rely a lot more than you might think on buoyancy effects of air bubbles in concrete to remove very, very large voids, and that buoyancy effect is not present in the space station, and it's only 1/6 of its strength on the moon as it is on Earth. The biggest problem with concrete, at least the way we normally think about making it, though, is that it requires water and it requires a lot of it. Now, we do have some water, like I said, at the lunar South Pole that you could conceivably melt. If you could find a way to keep it from boiling or refreezing, you could use it. The problem with water for concrete is that it's a reactant for the hydration process, which means that it's consumed. It's basically consumed and chemically bound into the concrete, and you can't recover it again without destroying the concrete. And if you talk to anyone at NASA, they're going to tell you that they need every little bit of water that they're going to be able to find on the moon to support human life and to make rocket fuel. So they've basically told the materials community that, hands off water. We're not going to let you use water in any extensive amounts to make material. So concrete, at least the way we think of it on Earth, is not going to work very well on the moon. So those are the chemical kinds of methods. You can imagine maybe geopolymerization or some other thing that's, adjacent to concrete, but these kinds of chemical methods are one way. The other main way that we have are thermal methods, which is the way that, for thousands of years on Earth, we've been making bricks and other kinds of things like that. The process is called sintering. And so sintering works by having a finely divided powder of material like an oxide of some sort or other. The nice thing is that it doesn't require any water. You can just fire it. If you can compact this powder together into a shape, you can heat it to a high temperature and you can get it to consolidate just by the application of temperature. So there's no water requirement. That's a big bonus. The nice thing about the minerals on the surface of the moon are that they have relatively low melting points. And so the temperature that you have to heat to is not even that high. So the energy cost is, it's high compared to concrete, but it's still manageable. And I'll talk a little bit about how we could achieve those high temperatures on the moon without too much effort. But the downside of sintering is that it requires you to really think about the particle size and shape distribution of the powder that you're using. Everything depends. The success of this method really depends on your ability to control the particle size distribution of the material that you're using. So let's look a little bit. I'm assuming that most of you don't have a background in sintering, and so I'm just going to spend a minute or two talking about how sintering actually works, just to get us all on the same page. And then I'll move on specifically to talk about sintering applications to lunar soil, lunar regolith. So the whole reason why sintering works is because the finely divided powder has an excess of surface energy embedded within it because the particles are so small. That surface energy, gamma, gives certain parts of the powder a high chemical potential and other parts of the powder a low chemical potential. So there's an automatic driving force for the material within the particles, within the powder or the block, like this brick. There's an automatic driving force for that mass to rearrange in such a way to reduce the overall Gibbs energy of the material. And it does that by reducing the total amount of surface area. So now this equation that I'm showing up here in the upper left is, you can call it different things. I call it the Gibbs-Thompson equation, but it tells us that the local chemical potential of material at any point within the system is going to be governed by the surface energy. So if you think of it like surface tension, and but multiplied then by the mean curvature. So anywhere you have very high curvature, the chemical potential is high. Everywhere you have low curvature, the chemical potential is low. So here's like a little cartoon drawing. If we looked under a microscope at particles within this block of material, you would see these two they're spheres, but like say you've got two spherical particles that are meeting together at a point. And so if you could get the temperature high enough, the atoms within this solid would spontaneously rearrange to go from places, I don't know if you can see my cursor, but it would go from places where the chemical potential or the curvature is high around on the particle surface into the region of contact between those particles where the chemical potential is low, because the curvature, although it's a large magnitude, it's negative. It has the opposite sign. And so material wants to spontaneously go there. And so what happens then, if you can get the temperature high enough, matter will diffuse from the particles to this region between them, and the particles will weld together. This, if you haven't thought about it before, the overall phenomenon is not that much different from what happens with oil vinegar salad dressing. So if you have a jar like this of oil vinegar salad dressing and you shake it up very high, you're supplying mechanical energy to the jar, and that mechanical energy goes into dispersing the oil and the vinegar into very fine particles. And that's what you're going to pour on your salad. But if you give it enough time, The oil and the vinegar, the surface between them has a surface tension, and so this material will spontaneously separate as a way to reduce that total amount of surface area or surface energy. And so even though this salad dressing is a liquid, the overall way of thinking about it is not that much different for salad dressing than it is for sintering of solids. Okay, so that's kind of how sintering happens or why it happens. I'll show you a brief video here, if I can, of this is a computer simulation of two particles that are sintering together, where the chemical potential is being mapped everywhere throughout this system. This is a simulation known as a phase field model, but you can see the two particles are the neck or the contact region between them is growing, and the two particles are approaching each other. Their centers of mass are approaching each other. So sintering actually causes not only a reduction in the surface area total, but it also causes a shrinkage of the material. And that's why we do it, is we want to eliminate as much of the porosity in the brick as we can by consolidating all of this solid into a smaller space and removing the porosity. All right, so let's see if I can get back. So the other question is, if we're going to use this method, how do we get the temperatures we need? And fortunately, we have a nice furnace in the sun that is continually bathing at least part of the moon in radiation. And so it's already been demonstrated in the literature that you can concentrate this solar radiation just like you do with a magnifying glass when you're, burning leaves on the ground as a kid. So you can concentrate this solar radiation into very fine points and achieve easily the temperatures that you need. You can think about doing this in kind of a 3D printing way, where you could redirect the focal point of the sunlight with a CAD program or something to be able to do something approaching 3D printing with a powder bed. Or you could imagine more traditional way of using the sunlight to heat up a volume of material like a furnace that's well insulated, and then sinter the material using the thermal energy that's bathing the entire interior of this room. So the ability to get the thermal energy is not as much of a deal breaker as you might think, and you can do it fairly cost-free as long as you have the instrumentation needed to redirect the sun's radiation. Okay, so now let's go and talk specifically about lunar regolith. So if you look up at the moon, you see two regions. When you look up at it, a full moon, there's kind of dark areas and light areas. The light areas that you see are the highlands regions of the moon, and they are composed primarily of a feldspar, just like we have here on Earth. It's a fairly pure feldspar, a northocite. It's a plagioclase, and it's crystalline. About 70% on average is this plagioclase, and the other 30% is a basaltic kind of, solidified lava that's kind of glassy, amorphous, and has lots of little minerals buried within it. So that's the light region on the moon. The dark region on the moon are these mare, the seas that you see, like they look like big swimming pools or lakes, and they are kind of inverted. They don't have very much crystalline material in them at all because they were formed long ago by very low viscosity lava flows when the moon was volcanically active. And so most of this material is basalt, which is really poorly ordered, has lots of little minerals in it and things like that. So we've got these two main regions on the moon, and so we wanted to investigate how the sintering, how sintering happens, or if we can even make it happen for these two kinds of materials. Now, we can't get the material directly from the moon. It's extremely expensive, and NASA doesn't just give it to anybody for any old reason. So we purchased very high fidelity synthetic lunar regolith from a company called Off Planet Research, and they can make material not only that's like highlands and like mare, but they will, and we have some, they can even provide material that simulates what was found at specific Apollo landing sites. So you can even get the variability of the different materials. You can purchase that as well. So these are some SEM micrographs of the two simulants that I'm going to be talking about, one highlands and one mare. We measure their particle size distribution. It came with some pretty coarse particles and pretty fine particles. The first thing we did, because we want high surface area and high surface energy, is we separated the largest particles away and retained the fine ones. And so these are the two particle size distributions that we ended up with afterwards. The blue is the Highlands and the red is the Mare. They're pretty similar in particle size distribution after we ground them down a little bit and remove those coarse particles. The way that we're measuring the sintering that I'm going to show, the experimental data that I'm going to show, the way we're measuring it is with optical dilatometry. The way an optical dilatometer, this is a picture of the instrument. The way the optical dilatometry works is I don't know if you can see it, but I don't know if you can see my cursor, but there's a part
Yes.
of it that's being pointed to called the specimen substrate. And so you can put specimens on this little stage. This big cage here, we can move it, we can translate it to the specimens, and it's a high temperature platinum furnace that can go up to 1700 degrees Celsius. And then we heat these specimens up, and we back illuminate them with a blue LED light. And there are 3 video cameras within the instrument itself that can capture the silhouette of the specimens as they're being heated. And so here's some actual pictures that were captured of these specimens. So on the left, we've got the Mare regolith. Anytime you see L, it means lowland or Mare regolith. And anytime you see an H in the name, that means Highlands regolith. So I'll show examples for each. But now you can see at each temperature, we can capture the silhouette of these cylindrical specimens. And so, and we can capture it continuously. And so we can measure the axial dimension Z and the radial dimension R both at the same time, independently of each other, as a function of time and temperature. That's really nice data to have. And the reason why is because if we can get both of these as a function of time, then we can measure the time dependence of the volumetric strain, in other words, the densification of this material, but we can also measure the creep strain. They're separable from each other. And in general, when you're sintering materials, creep is considered bad. Creep is a change in shape of the object without any densification or strengthening at all. So you would prefer to minimize creep and maximize the volumetric shrinkage. So we're trying to keep track of both. And we're mapping we're tracking the porosity of the material in terms of its relative density. Relative density just means its density divided by the density that it would have if there was no porosity at all. And so we can convert the volumetric strain into the relative density by this equation here. All right. So here are some examples of what we obtained with both the Highlands and the Mare regolith, plotting now the relative density as a function of time on the x-axis. And as you might expect, the higher the temperature is, the more densification behavior you get. You can get up to 90% of theoretical density, which means you only have 10% porosity left by the time the sintering is over. This is for the Highlands. For the Mare behaves a little differently. Even at relatively high temperatures, the density is kind of maxing out at about 75% instead of closer to 90%. I just want to make sure I show you that these little experimental dots that you see on each one of the curves, that represents 1 out of every 200 points that we obtain. So we're getting semi-continuous measurements, but the solid curves that you see are not the other experimental data points. They're actually a regression of all of the data to this logarithmic equation. So it's a very simple equation for the relative density as a function of time, natural logarithm, but it fits beautifully to all of the data. And that's been known for sintering since the 1950s. So this isn't something we discovered. We knew that it was going to behave like this, but it's gratifying to see that it behaves the way you expect things to behave. So now with this basic kind of raw data, we can now begin to look at things like the time rate of change of the density. We're really interested in the kinetics of this process. So we can get the densification rate by differentiating that regression model. And then we can recast the densification rate, not as a function of time, because who really cares about time? What we care about is how is the densification rate changing as the microstructure or the density of the material changes. So this is the relationship between densification rate and relative density. And you can see the plots of those here as well. it's not too surprising that the densification rate is a decreasing function of the density. And that makes sense because as we're densifying the material, we're losing that driving force for more sintering. We're losing surface area, and so there's not as much motivation for more sintering to happen, so the rate goes down, just like it does for diffusion or any other process. When you lower the driving force, you lower the rate. So we're now getting these densification rates. And from the densification rates, we can look at their temperature dependence. So, we plot just like you normally would with any rate process. We're going to plot the logarithm, the natural log of the rate on the y-axis as a function of 1 over the absolute temperature. And it's nice to see that the data do fit on a line, depending on, they all fit on a line for basically any experiment that we did. And the slope of that line then is the negative of the activation enthalpy over R. So we can figure out the activation enthalpy, the apparent activation enthalpy for densification for both the Highlands and the Mare regolith, which are shown here along with their uncertainties, about 400 and some odd, mid 400 kilojoules per mole. Which, if you're a cement person looking at hydration reactions, this is an extremely high activation energy. We're used to seeing things more like 40 or 50 kilojoules per mole because everything we do is near room temperature. But the activation energy for densification, solid state diffusion, is very high compared to that. And if you look in the literature, you can see these values in the mid 400s are on par with what's also been measured for the diffusion of silicon in plagioclase feldspars, which is basically the material that we have here. So we have some confidence that we're measuring reasonable activation energies by doing this. Looking, I don't know, what time is it here? Do I have like maybe 10 minutes left? Is that okay?
18 minutes.
18? Okay, perfect. So let's look at the microstructure here briefly. So these are SEM micrographs, both the backscattered image in the upper left-hand corner and then element maps on all the others. They're labeled. You can see what they are. What we consistently saw whenever we sintered these materials is we saw what looks like a matrix phase that has some porosity surrounding these relatively dense-looking inclusions. I can't prove it to you with this picture, but we've looked at these inclusions in the matrix, and the inclusions are not a single particle. They are a polycrystal of many of the fine particles that just happen to densify a lot more in that region than they did in the surrounding regions. So it's a polycrystal the whole way. It's just a different distribution of porosity in the inclusions than it is in the surrounding matrix. The reason I'm showing this picture is because we thought at first that maybe these inclusions are forming because there's a compositional difference, like these particles had material that had a lower softening point or something else that maybe made it densify faster. And you can kind of see for the most part that there's really no chemical difference at all between the inclusions and the matrix phase, except it looks like there's a little bit less magnesium. There's like a black spot in the middle of the magnesium graph. So there may be some gradation in the magnesium content, but we couldn't correlate that to anything that would cause a difference in densification behavior. If we look at the Mare now, the lower melting temperature material, we see almost the same kind of behavior. So you see these inclusion-like regions that are surrounded by less dense regions. And again, relatively little chemical difference between those two different regions, except again, the magnesium seems to be excluded within those regions compared to the highlands. All right, so we don't think that these heterogeneities are related in any significant way to compositional differences, but we do think we have an idea why they happen. And the reason why is something that's been known for a while in the sintering community, going back, several decades or more, and that's a phenomenon called differential densification. And the way differential densification works is that if you have a local gradient in the initial packing efficiency of the microstructure, like inside this red dash region here, then you have relatively more on average contacts between each particle and the other particles than you do around the perimeter of that red region. And so you can get faster and more complete densification of that region inside the red circle than you can the material on the outside. So the inside region separates away from the outside and you get a locally dense region compared to the rest. The same thing happens if instead of a packing density gradient, you have a size inhomogeneity. So if you've got a local region where there are some very small particles compared to a surrounding region, those small particles, because they have a higher surface energy, a surface area density, they will densify faster than the surrounding region. And again, you'll get this relatively dense region surrounded by a band of material that has relatively lower density. So we can even quantify this behavior in terms of something called sintering stress. So sintering stress is directly proportional to the local gradient in the chemical potential of the material. And so what you're actually seeing, and you can measure this with the right kind of a device, that when sintering is happening, you can measure the stress or the pressure that you have to exert on the material to prevent it from densifying. I'm going to say that again because it's kind of a weird thing to think about. If I've got a material that is sintering and trying to densify, I could grip onto it somehow and prevent it. I could constrain it from densifying, and I would measure an applied stress as a result of doing that. And that's what the sintering stress is. And we can actually calculate what the sintering stress should be for a given microstructure in terms of the chemical potential gradient. So these stresses are what pulls the microstructure apart in some ways, like I'm showing on the left, where local regions will separate because this stress is too much and it breaks the interparticle contacts, causing these inhomogeneities to form. So we really think this is differential densification that's causing these inclusions. I'm just going to wrap up this talk by talking about different ways that we can use sintering to do different things. So everything that I showed right now, that I've showed so far, when we think about sintering, normally we think about pressing a material into something like a cylinder, which is what I showed, or maybe a rectangular brick shape. And so pressing those particles together and then heating the brick up. And that's a perfectly legitimate way to do construction on the moon. I mean, after all, the Great Pyramids were made out of basically large bricks. So you can build almost anything like Legos if you have a bunch of bricks. And so you can imagine this like a sintering factory on the moon that just keeps putting out bricks, and then we can assemble different structures with the bricks. But it's also fun to think about ways to make more complicated three-dimensional shapes. And the way we've thought about doing it that we think is particularly adaptable to the lunar environment is a method called freeze casting. And the way freeze casting works is you take your particles, that's these gray spheres, and you make a slurry or a suspension out of them it's a water-based slurry. And hold on a second, I know I'm saying that we're going to use water to do this, and I'll come back to that because we have thought about that. So just give me a second. So you make a nice stable slurry, and then you freeze it. And luckily on the moon, we've got really low temperatures, a lot of the places that we want to do manufacturing. So we can freeze just by exposing the material to the lunar environment. When you do that, when you freeze it, the water actually, because of the anisotropy, the ice freezes in particular patterns. It forms anisymmetric crystallites that causes a really nice templating of the structure of the material into these different regions. And so once you've frozen it, you've locked in this microstructure, and now without melting the water, we're just going to expose it to the lunar hard vacuum and it will sublimate away. This is freeze drying basically. So we can sublimate all of the liquid, the ice water away, and we end up with a structure that has any shape we want because we can pour the slurry into a mold, and then we sinter it and we get the kinds of shapes that we want all in one step. And I don't know if you can see, I show a picture of it, but I brought some with me. So if you can, here's a freeze cast lunar regolith simulant little block of material. And here's a little gear that we made. All you have to do is just make a mold and cast the slurry into that mold. And then this freeze drying process will make materials. Here's one more. I don't know if you can even see this one. This is like a little threaded bolt. I don't know. Yeah, there it
Yeah,
shows
we
up a
can see
little
them.
bit. So like a little threaded bolt that you can see. So you can imagine making objects like tools and other kinds of complicated three-dimensional shapes without even having to go through the layer by layer kind of method that extrusive 3D printing requires. This is a one-step kind of process where the entire shape gets made all at once. So that's kind of that seems like a nice way to go. Now, the water, the nice thing about the water in this case, and the reason why we think it's legitimate to use it this way is because the water does not participate in any reactions. So when we sublimate the liquid ice, when we sublimate the ice away, we can recapture that water and we can use the same water repeatedly to just keep going. And conceivably, without losing hardly any water in the process, we can make multiple parts and we recover the water every time. So we think that this is a more acceptable way to use water on the moon because we don't have to keep asking for more all the time. It's a relatively low water supply. Okay, so we can do that. And then one other thing that we've done is we've looked at ways to make composite materials by freeze casting. We do the same process. We freeze cast the material into whatever shape we want, and then we do a very low temperature sintering to just get the particles to glue together enough that they can be handled. So we still have a lot of residual porosity in this material. And then we can vacuum infiltrate the material with another liquid that can be harvested from the raw materials on the moon, like sodium silicate. And we can vacuum impregnate this structure with this liquid, and then by heating it, by drying it, and then another low temperature or another low temperature sintering step, we can make these composite materials that actually have higher density and much higher strength than the original ones that we were making. And so here's some pictures of the kinds of objects that we've made depending on the way we did the infiltration. You can see down here that by doing this, we can again get relative densities way up around 90%, which in the moon's gravitational field gives us a good enough strength that we think that this will be a load-bearing material. You can see here the compressive strength of these objects are anywhere between 60 and 80 megapascals when we measure them. So since there's not as much stress on the moon because of the lower gravitational potential, we think that these kinds of strengths are probably acceptable for any kinds of load-bearing objects that you might want to make. All right, so I'm pretty much done. I'll just wrap up by giving you some ideas that I tried to get across. So we can just do normal pressureless sintering of lunar regolith. Interestingly enough, NASA, if you talk to them, they say sintering can't be done. It never works. It never works correctly at all. They keep saying that, even though I keep showing them that we can do it anytime we want. And I think the reason is because the people at NASA are, I got to be careful what I say. The people at NASA are really, really good with robots, making robots and using them and doing things like that. I don't get the sense that the people, even at Marshall Space Flight Center, really have the kind of knowledge of ceramic processing that would be required to properly do sintering. And so they basically just take the regolith and they just heat the crap out of it, and they notice that it doesn't work because they're not controlling the particle size distribution, they're not controlling the packing or anything else when they do it. And so they've come to the conclusion that sintering is not viable on the moon. And so we're currently in a bit of a struggle to figure out how to convince them that it is definitely viable, and they just need to learn some new things about it. Anyway, I've tried to show that we can get some fairly fundamental rate process information. We can understand the mechanism by which the sintering occurs. And more importantly, we can actually make parts. We've shown that we can do it. The only thing we haven't shown yet is that we haven't done it on the moon itself. So that would have to be demonstrated. But I really feel like this is at least a competitive way to make load-bearing materials on the moon. And so with that, I don't know, that's kind of all I wanted to say about it. And I'll just wrap up. And if you have any questions, I'm happy to try to answer them. If I said anything stupid, let me know and I'll apologize.